Hey everybody, welcome back. Today we're going to start Chapter 4, Chemical Bonding 1, the Ionic Bond Model. In Chapter 4, we're going to break this chapter into two main lecture components. The first one, we'll talk about chemical bonds, valence electrons and Lewis dot symbols, the octet rule, the Ionic bond model, what makes an ionic bond, how to figure out the sign and magnitude of charges on ionic bonds, and then Lewis structures for ionic compounds. And in the second half of Chapter 4, we're going to talk about the chemical formulas for ionic compounds, the structures of ionic compounds, how to name ionic compounds, including those that are binary ionic compounds, as well as polyatomic ions. We'll also cover naming hydrates and then writing chemical formulas and names for ionic compounds. So the whole second half is all about what we call nomenclature, how to name and write the formulas for ionic compounds. And the first half is introducing more of the concepts behind ionic compounds. So we'll get started at the beginning with sections 4.1 and a little bit of 4.4 as well. So most substances that we encounter in everyday life are compounds. And if we look at this diagram of matter, you remember back all the way back to Chapter 1, matter can be roughly divided into two groups, pure substances or mixtures. And then pure substances can be further divided into compounds or elements. So we start up here at matter. And if we're working with a pure substance can be an element, which is a substance just composed of one type of atom, like for example, pure copper, or it can be a compound. And in a compound, different elements combine in fixed definite proportions. And these atoms in a compound are held together by what we call chemical bonds. So chapters 4 and 5 are going to be focused on compounds, with Chapter 4 being focused primarily on ionic compounds. And then in Chapter 5, we'll talk about what are called molecular or covalent compounds in more detail. Compounds are classified as ionic or molecular compounds. So if we're looking at our flowchart again, and we're kind of zooming in to get more and more specific, we have a pure substance as our type of matter, and pure substances can be compounds or elements. And we've previously talked about elements, but remember, elements can be atomic elements, which means they're made up of just single individual atoms of one element, or elements can be molecular elements, where you have two atoms of the same element bonded together to make a molecular element. And these are the diatomic elements like oxygen and fluorine and bromine and chlorine, etc. Then on the other side of pure substances, we have compounds. And compounds can be further classified as molecular or ionic. Chapter 4 is all about ionic compounds. So ionic compounds contain one or more cations paired with one or more anions. And a cation is an atom that has a positive charge, and an anion is an atom that has a negative charge. And opposite charges in chemistry attract. So when you have a cation, an atom with a positive charge, next to an anion, an atom with a negative charge, those opposite charges are going to be attracted to each other. And that strong attraction due to the opposite charges is what makes an ionic bond. In most cases, the cations are going to be cations made from metal atoms, and the anions are going to be anions made from non-metal atoms. The other type of compound is a molecular or covalent compound. And again, these will be the focus of Chapter 5. And these compounds, molecular or covalent compounds, are formed from two or more nonmetals coming together and being attracted due to them sharing electrons. And the basic units of molecular compounds are called molecules. So some general properties of ionic compounds and molecular/covalent compounds. Ionic compounds tend to have high melting points of 500 to 2000 degrees Celsius. They tend to be good conductors in the molten or liquid state or when they're dissolved in solution. And the basic structural unit of an ionic compound is a repeating array of positively and negatively charged ions. So ionic compounds are again composed of cations and anions. Cations have positive charge, anions have negative charge, and the opposite charges are attracted to each other. And so these atoms or ions with opposite charges get pulled in close to each other, and that's what makes the ionic bond. And so ionic compounds are found as these repeating patterns of positive and negative charges. Where in this diagram here, let's say we have a negative charge, a positive charge, a negative charge, a positive charge, a negative charge, a positive charge. So one after the other. Think of like a checkerboard where you have a red square and a black square, a red square and a black square, or a chessboard where you have a black and white and a black and white. This repeating array of negative and positive charges being brought together due to the attraction of opposite charges is what makes up an ionic compound. Molecular compounds, on the other hand, have low melting points. They're often gases, liquids, or solids that melt easily. Unlike ionic compounds, molecular compounds don't conduct electricity very well. And the basic structural unit of a molecular compound is a molecule. So for an ionic compound, the structural unit is this repeating array of positively and negatively charged ions, which we'll learn is called a formula unit. Formula unit. And for molecular compounds, the smallest unit of a molecular compound is called a molecule. So chemical bonds are the attractive forces that hold two atoms together in a more complex unit, in a compound. And so chemical bonds can be caused by oppositely charged ions coming together, like in an ionic compound, to make these arrays of alternating positively and negatively charged ions. And chemical bonds can also be formed in molecular covalent compounds when atoms share electrons, and the sharing of electrons causes that attraction between the two atoms and pulls them close together into a chemical bond. We can have simple chemical bonds with, repeating arrays of positive and negatively charged atoms, two oxygen atoms sharing electrons and being bonded together. The water molecule, where an oxygen atom is sharing electrons with two separate hydrogen atoms, all the way up to getting into more complex biological molecules, all the way up to proteins and enzymes, and these larger and larger groups of atoms making up bigger and bigger molecules that make up all of biology. So chemical bonds form as a result of the interactions between electrons found in the combining atoms. So the ability to bond or not with another atom is linked to the electron configuration of each of the atoms involved in the interaction. And this is why in Chapter 3, we spent so much time focused on the electrons around atoms, where they're located, how much energy they have, how many electrons are in each shell and subshell, because it's those electrons interacting that determine whether an atom is going to form a bond or not. And there's two main types of bonds: ionic bonds and covalent bonds, which we also oftentimes call molecular bonds. So an ionic bond is formed when one or more electrons are transferred from one atom to another atom, or between groups of atoms. And so when electrons are transferred, that means that one atom is going to be losing an electron, and another atom is going to be gaining that electron. And so when atoms gain or lose electrons, they're gaining or losing negative charge, because each electron has a charge of -1. And so if an atom loses an electron, it's losing a negative charge, but the number of protons in the atom stays the same. And so that atom's going to become a cation or become positively charged. So in this example, we have sodium. And if sodium loses an electron, in this case, it's going to transfer it to chlorine, then sodium turns into a positively charged cation. It lost a negative charge. So it started out with 11 protons and 11 electrons. And when it lost an electron, it gave one away. Now it has 10 electrons and it still has 11 protons. So it ends up with a charge of +1. When sodium gives up an electron, it's going to give it to another atom that's going to accept it. In this case, that's chlorine. And the electron arrangement in the outermost shell of chlorine has 7 electrons in its outermost shell, or highest principal quantum number shell. it's ready to accept an electron. And we're going to talk more about this when we talk about the octet rule. And so chlorine readily accepts the 1 electron that sodium is donating. And so chlorine gains an electron. So chlorine has atomic number 17. So it starts out with 17 protons and 17 electrons. And it ends up with 18 electrons, and it still has 17 protons. So it ends up with a charge of -1. It has one more negative charge than positive charge. So overall, if you add up positive 17 plus -18, you get -1. Opposite charges are attracted. And so now we have one atom with a positive charge, the cation, and one atom with a negative charge, the anion. And these opposite charges are attracted. And the pulling together of this attraction is what forms what we call an ionic bond and keeps these atoms held tightly together in this chemical bond. For a covalent or molecular bond, these are formed when one or more pairs of electrons are shared between two atoms. And so what happens when a covalent or a molecular bond forms is that it's advantageous for both atoms involved to get another electron. And so instead of transferring from one to the other, they share the needed electrons between the two of them. So in this example, we have two hydrogen atoms. We'll call this hydrogen 1 and hydrogen 2. And hydrogen is going to be most stable if it has 2 electrons circling around it. And right now, each of these have 1. So if they each want to get 2, what they can do is they can each share their 1 electron with the other hydrogen. And so these 2 electrons are now shared by both hydrogens. It's like a win-win situation. So both hydrogens now have access to 2 electrons. And because the electrons are shared, it pulls those 2 hydrogen atoms really close together. They're attracted to each other so they can share those electrons. And that's called a covalent bond. And when atoms are brought together with this type of bond, it's called a covalent compound. We also call this a molecular compound. So let's do a quick concept check. An ionic bond is formed by which of the following? Sharing of 1 or more electrons between atoms, sharing of 2 or more electrons between atoms, transfer of 1 or more electrons from one atom to another, or transfer of 2 or more electrons from one atom to another. So hopefully, as you think this one through, you arrive at answer C, the transfer of 1 or more electrons from one atom to another. So the main difference between ionic and covalent bonds is ionic bonds involve the transfer of 1 or more electrons. And when one atom transfers an electron to another, you always form 1 cation and 1 anion. And then those opposite charges are attracted to each other, and that's what pulls them close to make a chemical bond, which we call an ionic bond. So ionic bonds are formed by the transfer of 1 or more electrons to make cations and anions, whereas covalent or molecular bonds are formed when atoms share 2 or more electrons. So if this question was asking you, a molecular bond is formed by which of the following? A molecular bond would be formed by answer B, sharing 2 or more electrons between the atoms. All right, next we're going to talk about valence electrons and Lewis dot symbols. This corresponds to section 4.2. So in order to talk about valence electrons and Lewis dot symbols, we first have to talk about the 2 fundamental concepts of bonding. So the first concept is that not all electrons in an atom are going to participate in bonding. And so the electrons that do participate in bonding are what we call the valence electrons. So it's just the valence electrons that are going to be the ones participating in chemical bonding, the ones that are either going to be transferred between atoms to make ionic bonds or shared between atoms to make covalent bonds. The second concept in bonding is that certain arrangements of electrons are more stable and therefore more likely than other arrangements. And the octet rule explains why some arrangements of electrons are more stable than other arrangements. So looking at the first concept of bonding, not all electrons in an atom participate in bonding. It's only the valence electrons. The valence electrons are the electrons that are located in the outermost or the highest energy electron shell. So when you're writing an electron configuration for an atom, this corresponds to all the electrons in the shells with the highest N number, the highest principal quantum number. Those are the electrons that are in the outermost shell, farthest away from the nucleus. And the farther away an electron is from a nucleus, the higher its energy. That's because the nucleus contains the positively charged protons. Electrons are negatively charged. Opposite charges are attracted. So the closer an electron is to the nucleus, the more attracted to that nucleus it is, and the tighter it's held onto by the atom. But the farther away the atom gets, that attraction gets less and less, the farther away the negatively charged electron is from the positively charged protons in the nucleus. So the electrons that are farthest away from the nucleus are going to be the highest energy, the most likely to be able to participate in a chemical bond, either by being transferred to make an ionic bond, or maybe accepting some electrons from another atom to make an ionic bond, or to be shared between two atoms to make a covalent bond. And so it's really important, and why we spent so much time in chapter 3 covering electron configurations and electron arrangements, is because by looking at those electron configurations, you can quickly see which electrons in an atom are the valence electrons, and therefore the electrons that are going to participate in bonding. So the number of valence electrons, the electrons located in the outermost or highest energy electron shell, can be determined from the atom's electron configuration. So the number of valence electrons that an atom has is equal to the number of electrons in the highest energy shell. On the periodic table, you can also quickly determine for main group elements the number of valence electrons by looking at the Roman numeral group number from the periodic table. I'm going to show you both ways to do this. And then in the middle of the periodic table, in the transition elements in the lanthanide and the actinide series, the number of valence electrons can vary depending on some special, what are called shell filling considerations. And we go more into this in Chem 400. But in general, the number of valence electrons corresponds to the number of electrons in the highest energy or the highest N value shell. So if we look at some electron configurations, here we have the electron configuration 1s2, 2s2, 2p6, 3s2, 3p2. Take a quick look at your periodic table and see if you can identify what element this corresponds to. Should be silicon. So if we look at the electrons in the highest energy shell, those are going to be the electrons with the highest N values. So if we circle the highest N values in our configurations, here we have an N of 3, 3s2, and here we also have an N of 3, 3p2. So all of the electrons in these highest N value orbitals are the valence electrons. So we have 2 valence electrons in the 3s subshell, and we have 2 valence electrons in the 3p subshell. So that means altogether, we have 4 valence electrons. If we look at another one, here we have the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p3. See if you can figure out what element this is based on its electron configuration. We know that it's an element that's at least 4 rows down on the periodic table because its highest principal quantum number is 4. We know it's on the other side of the D block because the 3d10 subshell is completely filled up. And it has 3 electrons in the 4p subshell. So if you count 3 boxes over from the end of the D block, you end up with arsenic. So this is arsenic. And this is just a quick way to also review what we talked about in chapter 3. So to figure out the number of valence electrons in arsenic, we count up the number of electrons in the highest electron shell, the highest N value. So if we find our highest N value, we have an N value of 4 here and 4 here. So all the electrons in the N equals 4 level are the valence electrons. So we've got 2 plus 3 is going to give us 5 valence electrons total. So you can always figure out the number of valence electrons that an atom has by writing its electron configuration and then adding up the number of electrons in all of the highest n value shells. The other way you can do it is you can do it using the periodic table. And I love showing things in the periodic table because even when you're taking a class in person, in future chemistry classes, when we're back to being in person, you're going to always have a periodic table in front of you when you take a chemistry exam. And so if you know how to do things using the periodic table, you don't have to remember these other tricks. You might not necessarily have to write out the electron configuration. You could quickly figure out the number of valence electrons just based on the periodic table. So the Roman numeral number system for the columns in the periodic table gives you the number of valence electrons for main group elements. So if we use the Roman numeral numbering system across here, this is group 1A, this is group 2A, then we have group 3A, then here we have group 4A, then we go to 5A, 6A, 7A, and 8. So the Roman numeral number corresponds to the number of valence electrons. So in group 1A, there's one valence electron. And in group 2A, all the elements in group 2A have two valence electrons. In group 3A, most of the elements in group 3A are going to have three valence electrons. Same thing, group 4A, 4 valence. Most of the elements in group 5A are going to have 5 valence electrons, 6, 7, and 8. And so by using the Roman numeral numbering system for the periodic table, it's a quick way to quickly figure out how many valence electrons an element is most likely to have. If we refer this also back to electron configurations, the S block elements are the first two columns of the periodic table plus helium. We know that an S subshell can hold up to 2 electrons. And so this corresponds to adding our first electron and our second electron. And so elements in the first column are going to tend to have 1 valence electron located in the S block. And elements in the second row of the periodic table, second column, are going to have 2 valence electrons located in the S block, along with helium. And then if we check out our P block elements, the P block contains 3 orbitals. It can hold 6 electrons. So if you count across the number of electrons that can be held, we have 1 electron here in the first column, 2 electrons in the valence shell in the second column, and then we go 3 electrons, 4, 5, 6, 7, 8 valence electrons total, if the S block and the P block are totally filled up. And so the total valence electrons possible for main group elements is 8. If all of their S block is filled up and all of their P block is filled up, they max out at 8. Because if you went to the next block down, the next series down, you'd increase the principal quantum number by going down a row. And so in general, elements can have up to 8 valence electrons. Main group elements can have up to 8. Transition elements generally also have 8, again, because there's some special filling exceptions. On occasion, transition elements will have a number other than 8 valence electrons possible. So Lewis dot symbols are just a shorthand way to display the number of valence electrons on an atom. And so to draw a Lewis dot symbol for an atom, you draw the chemical symbol for the atom, and around the chemical symbol, you put dots, and each dot represents 1 valence electron. And so in our representative or main group elements, hydrogen is in column 1A. It has 1 valence electron, so it gets 1 dot. Lithium is in the same column, so we expect it to have the same general type of electron configuration. Its highest energy electron, the last one added, is in the S block, and it gets 1 electron. And that's its 1 valence electron, so it gets 1 dot. Moving over a column in the periodic table, beryllium. It's in the second column of the periodic table. It's in group 2A. It has 2 valence electrons. So the Lewis dot symbol for beryllium is the chemical symbol Be with 2 dots around it. If you skip across the transition metals, that's what this zigzag shows, that we're skipping across the transition metals, going all the way over to boron, which is in group 3A. Or if you're numbering the columns straight across from 1 to 18, it's in column 13. Boron has 3 valence electrons, so it gets 3 dots around it. Next column over, starting with carbon. Carbon's in group 4A, or column 14 if you're just numbering straight across. It has 4 valence electrons. Nitrogen has 5 valence electrons, so it gets 5 dots. Oxygen has 6 valence electrons, so it gets 6 dots. Fluorine has 7 valence electrons. It's in group 7A, so it gets 7 dots. And then all the noble gases have 8 valence electrons, so they get 8 dots, with the exception of helium. And helium only gets 2 dots in its valence shell. I'll just circle this because this is the exception. Helium and hydrogen are the exception to getting 8 maximum dots, because helium and hydrogen are located in the first S block. We write their electron configuration. For hydrogen is 1s1. For helium, it's 1s2. And an S subshell can only hold 2 electrons. And so hydrogen, even if it completely filled up its S shell, its highest quantum shell, which is 1s, if it completely filled that up, it could at max hold 2 electrons. And helium also just has access to the 1s subshell. And so its highest quantum number is 1, its highest subshell, its subshell in that quantum number is an S, and an S can at max hold 2. So helium maxes out and is filled up with just 2. But all the rest of them, because they have 1 electron in the S, could have a second electron added to the S subshell, and then the P subshell can hold 6. 2 plus 6 in the P equals 8 max that they can hold. So Lewis dot symbols are a shorthand way to write the element symbols surrounded by dots that represent the number of valence electrons that each element has. So let's do a little bit of practice with Lewis symbols. Let's determine the number of valence electrons for each element below, and then draw the corresponding Lewis structure. And challenge yourself here to give yourself an opportunity to review from chapter 3. Could you write the electron configuration for each of these elements? So let's start with number 1, calcium. Calcium is an alkaline earth metal. It's in the second column of the periodic table in group 2A. So because calcium is in group 2A, the second column of the periodic table, it's going to have 2 valence electrons. So to write its Lewis dot symbol, we write Ca with 2 dots to show its 2 valence electrons. You'll notice in your homework for this class, as well as in the textbook, most of the time they're going to write the Lewis dot symbol for calcium with the 2 dots separated. But sometimes you will also see it written like this, with the 2 dots next to each other. This is also the way you're going to most likely see it when you take Chem 400, with the 2 dots next to each other. And that's to show that these 2 dots are in an S subshell paired together in that S subshell. Both are technically correct, but I just want to highlight that you might see some slight differences with where the dots are located. Your textbook uses both methods. The online homework system may use both methods, but then in future classes, if you take Chem 400, you'll probably see this method being the one that's preferentially used, because it gives you a hint that those 2 electrons are paired together in an S subshell. Okay, and if we wanted to write the electron configuration for calcium, just to get a little extra practice for that, it'd be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And so the highest energy shell The highest principal quantum number is 4. It's in an S subshell, and there's 2 electrons. So there's 2 valence electrons in calcium. Okay, let's do neon next. So neon is in group 8A, or column 18. It's a noble gas. So it's going to have 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. The reason I filled them that way was, again, to kind of remind myself that these electrons are filling into subshells. And as you look at the periodic table, the electrons, the valence electrons in neon are going to first fill up for neon, the 2s2 subshell, and then these other 6 electrons are in the 2p6 subshell to get 8 electrons total. And if we wrote the electron configuration for neon, it'd be 1s2, 2s2, 2p6. You can see that's 8 valence electrons. And so neon gets 8 dots around it. Okay, let's do silicon next. Silicon is in group 4A, column 14, so it's going to have 4 valence electrons. Could be written that way with all 4 spaced out, or if you want to show that those first 2 electrons are paired together in the 3s2 orbital, you could put those 2 next to each other and then put the other 2 separated. And again, that's to remind yourself that if you were drawing the electron orbital diagram for silicon, the first 2 valence electrons and the 3s subshell would be paired together, and then the next 2 electrons would be in the 3p subshell, and they'd be in separate boxes, so you draw them on separate sides. Okay, bromine. Bromine is in group 7A. It's a halogen, so it's going to have 7 valence electrons. And you draw it like that. So you should be able to draw for all of the main group elements, the Lewis dot symbol showing the number of valence electrons. And again, between your homework and the textbook, and especially if you are going on to Chem 400, you may see some slight variations in the ways these are drawn, whether the dots are just evenly spaced out, or if the first 2 dots are paired together to show that these 2 electrons are being put into an S subshell, and that S subshell is completely filled up with 2 electrons before you start filling the P subshell. Okay, so some key things to remember about valence electrons. First thing is the periodic table is arranged so that elements with similar electron configurations are grouped together in columns. So the elements in the main group section of the periodic table, all the elements in the same column have the same number of valence electrons. The number of valence electrons for the main group elements is the same as the Roman numeral group number on the periodic table. So if you number the periodic table according to the Roman numeral system, all the elements in the A section, like group 1A, the alkaline metals, group 2A, the alkaline earth metals, the Roman numeral number gives you the number of valence electrons. The maximum number of valence electrons for main group elements is 8. And this is because for main group elements, when you're filling their electron orbitals and writing their electron configurations, the highest quantum numbers are always going to correspond to an S subshell and then a P subshell. And an S subshell can hold 2 electrons, and a P subshell can hold 6. So 2 plus 6 equals 8. That's the maximum number of electrons that could be in that highest principal quantum number shell. And the S and the P shells are always going to have the highest principal quantum number, because when you get to the D and the F subshells, when you're coming up with their principal quantum number, for the Ds, you have to take the row number -1. And for the F subshells, you take the row number -2. So the S and the P subshells are always going to have your highest principal quantum numbers, which means that the most electrons that could be held in the highest principal quantum number shell is always going to be 8, because the S and the P subshells can hold up to 8 electrons altogether. And again, the exception to that is the first row of the periodic table with hydrogen and helium. And this is because they only need one single s orbital, which can at most hold 2 electrons, to fill up their highest energy, highest n value electron shell. They only have a principal quantum number of 1. 1s is their highest energy orbital, and that can at max hold 2 electrons. So they could have up to 2 valence electrons. All the other elements can have up to 8 because their highest principal quantum number shells will always be able to hold up to 8 electrons. And again, there are some exceptions in the transition metals due to some unique filling orders. But for all the main group elements, the max number is 8. All right. Next time, we'll talk about what's called the octet rule, the sign and magnitude of ion charges, and isoelectric species. Thanks for listening. Bye.